Okay, hi everybody, and welcome to the second in our series on LCDM and the Hubble assumption. Today we have Eleonora Di Valentino, who is a Royal Society Research Fellow at the University of Sheffield. She's worked extensively in the science collaboration and also written on the Hubble assumption. And today she's going to be telling us about anomalies and tensions in cosmological data, challenges, and insights. Thanks, Eleonora.
Thank you so much. Thanks a lot for the invitation. Okay, so I will talk about the Hubble tension and in general the anomalies and tensions during the cosmological data. So let me start with introducing the Lambda Cold Dark Matter model because we assume this model as the standard model of cosmology, but actually this is based on three completely unknown quantities that are inflation, dark matter, and dark energy. And we have chosen this model because this fits in a very good way the data. But then for these three quantities, we are considering the simplest possibility. So the inflation is as a Rho-Rollins scalar field. Dark matter is pressureless and cold and interacts only through gravity. And dark energy is a cosmological constant term. So this seems more a fitting model, and this is an approximation of an underlying theory yet to be discovered. So with the improvement of the measurements, we expect deviations from this model. And the fact that we start to see now tensions and disagreement between some of the parameters obtained from different experiments can indicate that we need to change the Lambda Cold Dark Matter model when we analyze the data. In particular, the most significant tension we have today in the data is the Hubble constant tension between that it can be measured historically in two ways. First of all, we can measure the luminosity distance and the recessional velocity of unknown galaxies, and in this way, and this is called the Hubble law, and then we can compute the proportionality factor, and this will be the Hubble rate. This is of course, valid, just a very low redshift, okay? There should be at higher redshift corrections to this. And then the second way, so this is a direct measurement of the Hubble constant. And the second way is that measuring something that is in the early universe, like the CMB, the cosmic microwave background, and assume an expansion history of the universe. And we assume the standard model, so the first Friedman equation. And this way we estimate the value of the Hubble constant. So now this tension is at the level of 5 sigma, and between the disagreement between these two methods. On one side, we have the Schuss collaboration result, and on the other side, we have instead the Planck estimate of the Hubble cost, assuming the Lambda Cold Dark Matter model. So the local measurement, the Schuss collaboration is based on a distance ladder, okay? So that Dan explained this last week, so I will go through it quickly. We can calibrate the surface using parallaxes, eclipsing, detached eclipsing binaries, and water masers, and then we can use the surface that are pulsating star to calibrate the Tephany supernovae that are instead exploding stars, and then we can use the Tephany supernovae in the third rank in the Hubble flow, and in this way we can derive constraints on the Hubble constant. So these are the three ranks, and what the Schuss collaboration has done is to consider fit all the three ranks at the same time. For this reason, they have such an amazing constraint on H naught. And now with the new measurement, considering a fourth anchor, they arrive a very strong constraint on the Hubble constant. So the tension with the Planck measurement is at the level of 5.8 sigma. On the other side, we have the CMB constraints. In this case, what we see is that we assume a model. So the CMB is the radiation emitted at recombination about 400,000 years after the Big Bang. This CMB, okay, is homogeneous and isotropic, is a black body spectrum because it preserves the photons preserve the shape of the primordial plasma which they were in thermodynamic equilibrium. But then we have small anisotropies of this on this black-body spectrum of the order of 10 to the minus 5. And these anisotropies are the seeds that then will grow in structure, but also keep track of the history of the universe. They are so-called secondary anisotropies. So we can expand the Legendre polynomial, the two-point correlation function between the difference of temperature and two direction in the sky, averaging on the total sky, and we obtain the well-known temperature power spectrum, where the red dots are the data obtained by Planck in 2018, and the blue line is the model that we are going to fit. So how we can, in this case, constrain the parameters? What we do is to choose a set of cosmological parameters. So assuming the Lambda Cold Dark Matter model, we have 6 independent cosmological parameters. Then we vary these parameters to see the effect on the temperature power spectrum. And what we see is that varying the parameters, we have a changing in the amplitude and position of the peaks. So at this point, we have to find the best combination that best fit the data, and we do this using a Bayesian approach and MCMC codes. So we assume a Lambda Cold Dark Matter model, we use our MCMC codes, and we obtain these constraints on the model. So at this point, we say, okay, this is a wonderful confirmation of a flat Lambda Cold Dark Matter model, because we have many sigma of indication for a cold dark matter different from 0. The scalar spectral index is almost 1, but not exactly 1 for the dynamics of the inflaton field. So we say, okay, this is a confirmation, but we have to be careful, because in this case, we are assuming a cosmological model. So if we change the model and we fit the same data, we will find completely different results. And then there are correlations between the parameters that can bias the results in one direction. So at this point, what we need is other Hubble constant estimates, and these are the latest ones, okay? I collected here the latest ones. So on this side, we have the indirect measurements that are assuming a Lambda Cold Dark Matter model, and on this side, the direct ones, okay, that are Lambda Cold Dark Matter independent, so direct measurements of the Hubble constant. So as you can see, okay, these are always preferring a higher value, while the indirect ones a lower value. In particular, okay, for the indirect measurements, we don't have just Planck, but also the other CMB ground-based telescope, like the Atacama Cosmology Telescope, that is giving H naught always around 67. And we have also the Southport Telescope that is giving around 68. So they are very well in agreement with the Planck result. And they are always assuming a Lambda Cold Dark Matter model for fitting the data. But we have also the spectroscopic survey BAO full shape from BOSS and DBOSS. And in this case, this can be combined in different way with BBN, with CMB, and all of them are in agreement with the lower value of the Hubble constant as well. And all of them, again, are assuming a Lambda Cold Dark Matter model. On the other side, in the direct measurements, we have the type 1a supernovae calibrated with the Cepheids, and this is the SHOES result. Okay, and here I'm reporting also the latest JWST measurements that came out in August. Then we have the type 1a supernovae calibrated with the tip of the giant star, and where, okay, these are the old Friedman et al., and then there are the new measurements with the other teams, and these are again the new JWST values. Then we have the type 1a supernovae calibrated with a combination of Cepheids, tip of the giant branch, surface brightness fluctuations. And as you can see, they are very much in agreement with the Necker value of the Hubble constant. This is the Friedman's group, and using again the HST measurements. Then the type 1a supernovae can be calibrated with MIRAS, that are variable giant stars. Then there is this new method that is JAGB, that is based on carbon-rich stars. Then the type 1a supernovae can be calibrated again with a combination of Cepheids, TRGB, and JGB, and these are new results based on the JWST measurements. Then there is this combination of DESI, fundamental plane of DESI, and the distance of coma. This has been discussed in detail by Dan last week, and these are reporting a higher value for the Hubble constant. Then there are masers. In this case, there is not a distance ladder, so directly the Hubble flow is used, and This is always in agreement with an value for the Hubble constant. Then we have the measurement based on the Tully-Fisher relationship. Again, if this is using the third rank, we can calibrate them with Cephas and TRGB, and they are always in agreement with an value for the Hubble constant. Surface brightness fluctuations that can be calibrated again with Cephas and TRGB, and finally type 2 supernovae. Now, as you can see, okay, all of them agree with an eigenvalue of the Hubble constant, and then has been discussed like the new JWST measurement are very big error bars, okay, but a better way to see this measurement is comparing with the same measurement made by HST, because what WST is measuring is not new objects, they are old objects that have already been measured by HST, but while HST had 42 supernovae and 4 anchors, with JWST they have just 10 supernovae, 1 anchor. So if we are going to consider exactly the same objects and we estimate the Hubble constant with HST, we have these top error bars, while the lower ones are the one, sorry, the opposite. The lower ones are the one estimated with HST and the top with JWST, and you can see that they are very much in agreement. So the results from JWST are not unexpected, they are cross-checked, and they are perfectly confirming the HST results. And now if you combine together the two teams, the shoes and CCHP, you see that these are the new value obtained by JWST, that is 72.6 plus minus 2 kilometer per second per megaparsec. So the interesting point, in my opinion, is that if we have a true measurement of the Hubble constant, a true value, what we want to see is a scatter around this true value, but this is not what we see. We see all the direct measurement on the higher side and all of the indirect measurements on the lower side. So in my opinion, this Hubble tension is very robust, and this is the puzzling result. So just removing one of the measurements, even if there are systematics in one of the measurements, this is not gonna solve the Hubble tension at all. There could be, of course, systematics in the different experiments, but at this point we should understand why they are biasing the results all in the same direction. So another alternative that is very easy to think is that we are just choosing the wrong model when we are considering the indirect measurements of the Hubble constant. So let's try to modify the Lambda Cold Dark Matter model and see if we can solve the Hubble tension. We'll see that this is very complicated, not because the important thing is not the value of the Hubble constant, but all the additional things that we have to take in mind. The first one is the sound horizon problem, because, okay, there is not just CMB, there is not just supernovae and distance ladder, but there are also the baryon acoustic oscillation data. And these BAO data combined with Pantheon, okay, this is a supernovae sample, they are measuring the product of the Hubble constant and the sound horizon. So you can see that this green band here. So they don't really measure these two things separately, but if we want to be in agreement with an eigenvalue for the Hubble constant like shoes, we need a lower value for the sound horizon. If we want to be in agreement with the CMB measurement of the Hubble constant, we need an eigenvalue for the sound horizon. So at this point, when we try to change the Lambda Cold Dark Matter model, if we consider modification in the late time, and for late time solutions, we indicate modification of the expansion history after recombination. Of course, the sound horizon and the recombination will be fixed. So what we can do is just increase the Hubble constant, because we are decreasing the expansion history and intermediate redshift. But this is not gonna be in agreement with the measurement of BAO and supernovae. One example is replacing the cosmological constant with a dark energy that has an equation of state free to vary. So we can solve the Hubble tension within 2 sigma if we have a phantom dark energy. Okay, phantom dark energy means a lot of theoretical problems because it's violated the Lund energy condition, but we can always think about a model that behaves effectively as a phantom dark energy, doesn't have the theoretical problems. So something that works very well for the CMB, for Planck, it doesn't work when we consider the low redshift measurements. So as soon as we add the BAO data or supernovae data, the cosmological constant is back in agreement with the measurements, and we have again the the Hubble tension that is increasing at more than 3 sigma. And this is because something that is undistinguishable for the CMB, so is the best fit from Planck alone is the dashed line here, is very much different from the best fit considering Planck plus BAO, that is the solid line here. And we can see that the difference is much larger than the error bars of the BAO data itself. So every time we try a late time solution, at the end we discover that this result that are good for the CMB alone fails to recover the shape of h of z at low redshift. So if the late time solution don't work, let's focus on the early time solutions. In this case, we can at the same time lower the sound horizon and increase the value of the Hubble constant. But what we see is that if we don't add a prior on H naught, so the error bars are very much increased. So the contour plots are always around the Lambda Cold Dark Matter model. We have, in a few words, a volume effect. So we increase the error bars of the Hubble constant, and now we reduce the tension with the value measured by shoes. But if we don't add a prior on the Hubble constant that is dragging the H naught measurement towards shoes, the tension is still there. And one example is when we vary the neutrino effective number, because, for example, we assume that there is extra radiation, or when we consider the early dark energy. So early dark energy, we have an extra scalar field that is accelerating the universe before recombination. And if we want the effect that can lower the sound horizon to be in agreement with the low redshift measurements, the mass of this scalar field should be of the order of 10 to the minus 27 eV. And this is why the first proposal was an axion particle. Okay, an axion-like particle, because the exponent should be different from 1, because this should be redshifting away very quickly to avoid to spoil the late time universe. So if we have an early dark energy model, okay, and we look just at the Planck CMB measurements, we see that we have just an upper limit for a fraction of early dark energy, but the Hubble constant value is not changing. So the tension is still at the level of 3 sigma. This is again, okay, because to move the Hubble constant towards a higher value, we need to add the Hubble prior on the measurements. So a very important thing will be able to have a measurement of the sound horizon that is independent from all of these. And we forecasted that this will be possible to reach an accuracy on the sound horizon 1.5% if we are going to combine gravitational wave standard sirens with the BAO, angular BAO. That means only the BAO on the shells, okay, where we are not reconstructing the distance from the redshift. So this is the same plot as before, okay? These are the Planck results. This is shoes, and the gray band is the combination of BAO and supernovae. So if we want to move the constraints along this line to be in agreement with all the measurements, and you can see that if we have 1.5% of accuracy on the sound horizon, we will be able to rule out the resolution of 4 sigma or to confirm the resolution at 4 sigma. Okay, so now, we said that the late time solution don't work, but unfortunately also the early time solutions have some problems. And one of these is the S8 tension, where the S8 tension is the second most statistically significant tension we have in cosmology. S8 is a parameter defined as a combination of the clustering parameter and the matter density that is used to quantify the tension that we see in this plane between the value measured by Planck, assuming a Lambda Cold Dark Matter model, and the value measured by the weak lensing experiments. This is a combination of Kids Viking 450 and BOSS, and you see the tension is at the level of 3.1 sigma. Then we have, 3.4 sigma. We have 3.1 sigma for Kids 1000 alone, that is the red contour. Then we have 2.5 sigma for this Y3. and 2 sigma for HSC Y3. And here I like this plot because, as you can see, that's Y3 and kids, they overlap perfectly. So why we are quoting different tension with Planck? Because we are using different tools, and this is another thing we have to think about when we work with trying to solve the tension. For DES Y3, they are considering the whole volume of the parameter space, and they're using the suspiciousness statistics, so they quote 2.5 sigma disagreement. For kids 1000, they're just looking at the value of S8, and they quote 3 sigma disagreement. For me, the interesting thing is like before, because also in this case, we have that the early universe measurement that here are just CMB measurements prefer a higher value for S8, while the late universe measurement prefer a lower value for S8. And here we find with cleansing galaxy clusters counts and redshift space distortions data. Here, this is different from the previous one because for the Hubble constant, we have direct measurement that are Lambda Cold Dark Matter independent, and then the indirect ones that are Lambda Cold Dark Matter dependent. Here, all of these measurements are assuming a Lambda Cold Dark Matter model, and they disagree. So the late universe and the early universe disagree, even if they are assuming the same model. So now, what is the problem when we try to find a solution for the Hubble constant? This is again the same plot. So we want to be here in agreement with a higher value for the Hubble constant and lower value for the sound horizon, where we are moving along this line of correlations, where in particular this green one corresponds to a much higher value of omega m h squared. Now, omega m h squared is a quantity that is measured accurately well from the CMB because it's measured for the peak structure in the damping tail. So if we are in agreement with more matter, what we find out is that we will have this corresponds to the model 3 in this plane here, so we are exacerbating the S8 tension. So with the early time solutions, we are worsening the S8 tension, even if we solve the Hubble constant tension. So when we look at a solution, we should always keep in mind that we should be careful about the triplet H0, sound horizon, and omega matter at the same time. And if we do, if we consider this, okay, if we look at this plot, this has 180 data points that are the models for which we could find the estimates for the Hubble constant, the sound horizon, and the matter density. The models proposed to solve the Hubble tension are now, because this is 3 years old, now are at least more than 500. For these 180 points, there is none of them that is at this intersection here, So none of the models proposed in the literature can solve the Hubble tension and be in agreement with all the data available at the same time. Okay, so now I want to show a few examples. Because I found this interesting and also because I work on them. So these are the interacting dark energy model, dark matter, dark energy. In this case, we are modifying the conservation equation, assuming an interaction rate that is proportional to the dark energy density, the conformal rate, and the coupling, and then using this negative parameter psi that is quantifying the strength of the coupling. Okay, this is useful to solve the Hubble tension. If you modify any of these ingredients, it doesn't work anymore. And these are not theoretical explanation at all, okay, just phenomenological. Okay, I like to present this. Okay, first of all, we have that in this model, we have just an upper limit for the matter density because we have a flux of energy between dark matter and dark energy, so we lower the matter density. Since we are measuring this quantity very well, omega m h squared, if we have less matter, we have a higher value for H0 naturally. So we can solve the Hubble tension not because of larger error bars, but because of a stronger overlap. And in this case, if we add a prior on H0, we have 5 sigma indication for a coupling different from 0. And the S8 tension is not defined because the Planck constraints that are very small now are relaxed and shift in agreement with the dark energy survey. So what we want to do, first of all, when we propose a new model is to do a model comparison. We can use the Bayesian evidence that is based on the Occam's razor principle. So if the model is more complicated, we have more parameters, so we want this to improve significantly the fit of the data to be favored. And we use the bias factor to compute the Bayesian evidence too. So we are going to compare with the Jeffrey scale, and we will have a weak, moderate, or strong evidence for model 0 against model 1 depending on the value of the bias factor. If we do this for the interacting dark energy, from Planck alone we have a weak evidence for interacting dark energy, and combining with the prior coming from shoes, we have a strong evidence for the interacting dark energy. At this point, what we want to do is to cross-check with the alternative CMB data, and now it's possible because we have the Gamma Cosmology Telescope, for example, and this is important because they're measuring different scales. Planck goes from 2 to 2,500 multiples, ACT goes to up to 4,200, but is missing the first two peaks, so then we want to break the correlation between the parameters, adding something in the low multiple region, and we can do this adding the full WMAP data, or Planck up to multiple 650 to avoid the double counting in the region that they have in common. So if we do so, we see that H naught is naturally in agreement with shoes for all the datasets combination, and we have a coupling that is different from 0 at the level of 1 to sigma. So, and this stronger indication is coming from the high multiple region. Okay, you see that with the interacting dark energy model, we are going a bit down, so closer to the data in the high multiple region, and this seems large error bars, but because we have a log scale, actually they're very, very small. So now the point, okay, we solved the tension, we have this model that works very, very well. But no, because this is the first problem. Another problem that we have is that we should always cross-check with simulations. In this case, we simulated an experiment like Planck, assuming no interaction between dark matter and dark energy, so they are not coupled in the real world. But then we analyze this fake mock dataset, like assuming the possibility of an interaction between dark matter and dark energy, and we see that we have a fake detection of more than 3 sigma for a coupling that is not in the fiducial model. So the posterior is skewed towards negative values, and this is just due to the correlation between the parameters. So what we need is to add BAO data, low redshift data, to break the correlation. These are simulated as well, and we see that we can recover just the lower limit again. So now what happens when we add real data, real BAO data to the real CMB data? We have just 1 sigma for a coupling different from 0, and we have H naught that is about 70. So we have 2.1 sigma tension with shoes that can mean a residual tension or a statistical fluctuation. And this is difficult to say because now we are always considering the BAO data as they are, but they are formed in the early universe and we are measuring them in the distribution of galaxies. So it is possible that they can't really be used as they are when we consider a model beyond Lambda Cold Dark Matter, okay? Because we are assuming as a fiducial model Lambda Cold Dark Matter in many points of the data reduction process. In the fiducial model, in the covariance matrix to estimate the errors, and in the reconstruction between the redshift and the distance. So they have been tested the reliability of BAO for models that are going to modify the expansion history before recombination, and for models that modify the expansion history after recombination, that are, for example, can be parameterized by W0WA, but okay, and they are being tested if we are around Lambda Cold Dark Matter within 5 sigma, but if we are very much far away from Lambda Cold Dark Matter and the growth structure is different, it's possible that they should be revised. So test that we have done is to, instead of considering the 3D BAO data, to consider the 2D BAO data, where we are neglecting one of the assumptions, so we are not doing the reconstruction between the redshift of the distance. So the error bars will be larger and we expect the results to be more conservative. If we assume a Lambda Cold Dark Matter model and we do a comparison with the 3D BAO and the 2D BAO, we see that H naught is very much in agreement. They are in agreement one with each other. But if we introduce the interacting dark energy model, we see that H naught goes up. Again, now we are able to solve the Hubble constant tension. We can add a prior on H naught, and again, we have an interaction of more than 5 sigma. possibility is that, okay, we are using a sample that is the National Observatory in Brazil that is different from the sample used from the 3dBO. So if instead of using this 2dBO, we use the Menot and Marra sample, we see that the Hubble constant is exactly the same. So even if we are allowing more flexibility because the error bars are larger and the results should be more conservative, they're exactly the same using the 3dBO and the 2dBO, assuming a Lambda Cold Dark Matter model. But if you assume an interacting dark energy model, you have again a shift towards higher value of the Hubble constant. And again, and we have an interaction at 1 sigma between dark matter and dark energy. So the take-home message here is that when we say that the late time solution are ruled out, we should be careful in understanding if the BO data can be used as they are, or we should re-extract them assuming the new model. So now, to add some spice to the problem, we have the new DESI-BO data, where we have an indication 3.9 sigma for dynamical dark energy, replacing the cosmological constant. And first of all, we checked that if this is robust, and and so we try to change the parameterization instead of using the CPI parameterization, different kind of dynamical dark energy models. And you can see that this is very robust. So the dynamical dark energy indication more than 3 sigma is still there. And at this point, so we try to use this new DESI-BO data with interacting dark energy model, and we see that we have 2 sigma for a coupling different from 0, and Hubble constant again in agreement with the Schuss value. The chi-square is improving, but the Bayesian evidence is undistinguishable. So this interacting dark energy model with the new DESI-BO data is providing a better fit of the data. From a Bayesian point of view, they are all good, but it can also solve the Hubble constant tension. Another possibility, okay, at late time is to consider another model, okay, that we called omnipotent dark energy. This kind of models, okay, can have a very complicated dark energy sector where the dark energy density can be negative, non-monotonic, oscillatory, the equation of state can be phantom, quintessence, so we can cross the phantom dividing line, there could be singularities, and all of these features are present in at least one point of the parameter space. So one possibility, okay, in this class of model, we find this simple expansion, Taylor expansion of the dark energy density around the possible extrema. And okay, this will be the expansion rate of the universe and the dark energy equation of state for this model. And if we are going to fit the data, we see that the Hubble constant is higher in agreement with the Schuss value if we have a phantom crossing of more than 2 sigma. This is true also for the new latest measurements, and this is just because we don't have, the dark energy is not monotonic. And this is fitting the BAO data better than Lambda Cold Dark Matter, as you can see. And so this is a combination of latest, where these are the old BAO data or the latest measurements. So you can see this phantom crossing model fits the BAO data better than Lambda Cold Dark Matter. So again, it's possible to have a late time solution that can solve the Hubble tension if, for example, we have a non-monotonic dark energy density. And in this case, this model has been tested also independently by another group with the SPT data, and you can see it can also solve the S8 tension. Finally, I want to show you the latest, another late time solution that is a sign switching cosmological constant. So we start with a negative cosmological constant at a certain point, switch to positive to have a positive cosmological constant today. And you can see that the value of the Hubble constant is higher for this model if the switching is happening at the redshift equal 1.7. And interestingly, if we use this 2dBAO data, and you can see that the 2dBAO data constraints and the Planck constraints are intersecting exactly on on the value of shoes, of the shoes collaboration, the Hubble constant measured by the shoes collaboration. And here we can see the comparison with the weak lensing data. And from Lambda Cold Dark Matter, we have this tension. This is not present anymore for the sign switching model. So this is just phenomenological, and this case is working because we have a negative cosmological constant in the past. So again, this is in agreement with the data because of a strange dark energy sector. So this was just phenomenological. A few try of theoretical explanation came out. The one we worked on is based on type 2 minimally gravity models, where this cosmological constant has been upgraded to a potential. And if the potential is this shape, for example, of a scalar auxiliary field phi that is rolling down the potential, when the potential change slope, we have this abrupt change of the cosmological constant from a negative to a positive side. So this is an effective cosmological constant. This actually then has problems because we have singularities and in each dot, so the perturbations don't really work. So we can't use this potential as it is. What we can do is instead considering instead an abrupt change of sign in the cosmological constant, something that is a bit smoother, that become the sign switching if eta goes to infinite. And in this case, we can reconstruct the potential. We call this kind of model lambda S VCDM. And this is just to say that this model works very well again with the local measurements, can improve the fit of the data, can solve the Hubble constant tension, and can also improve the S8 tension. So again, the late time solution as they are, they don't work, but as soon as we introduce a different dark energy sector that can be negative, non-monotonic, or an interaction between dark matter and dark energy, the late time solution are back in the game. Now, until now, we always think about possible systematics when we try to solve the Hubble tension in the astrophysical measurement, but actually there could be a possibility that the problem is on the CMB side. And we know that because there is the famous A-lens problem, where A-lens is a amplitude that has been introduced in front of the lensing potential. This amplitude is expected to be equal 1, and we can measure the amplitude through the smoothing of the peaks in the damping tail. So if different from 1, we are in presence of systematics or new physics. And if we measure A-lens from Planck, we have that this is larger than 1 at the level of 2.8 sigma, with an improvement of the chi-square on 910 depending on the datasets used. And it's not a true measurement of the lensing that can instead be done with the 4-point correlation function, for which A-lens is exactly equal 1. Now, if this is a systematic in Planck, we marginalize over this systematic, and we can see that because of the strong correlation with S8, we can solve completely the tension with the weak lensing measurement, and the A-lens is larger than 1 and more than 3 sigma if we add BAO and supernovae data. So we don't have any more S8 tension with Planck, which happens with the other CMB experiments. From ACT is at the level of 1 sigma, so it's not significant. From SPT, they overlap one with each other, so there is no tension at all. So now, what if is not a systematic is an indication of new physics having a lens different from 1? Yes, the simplest possibility is that we have a curvature of the universe, and if we let the curvature free to vary, we have 3.4 sigma indication from Planck. And again, so the first question is, okay, but this is maybe due to the correlation between the parameters as we saw before. So we simulated an experiment like Planck, again, assuming a flat universe, and we have that we can recover omega k equals 0 with a 2% uncertainty. So this measurement of omega k less than 0 is not due to the degeneracy between the parameters, because the gravitational lensing measured by the temperature power spectrum, so embedded in the temperature power spectrum, is enough to break the correlation and give us a measurement of omega k. So we are not only fitting the damping tail like a lens, but we're also recovering the low anisotropy quadruple. So this is why with omega k we improve the chi-square of 11 instead of 910 like a lens. So now there is a strong correlation between these two parameters because if we have a closed universe, we have more matter. More matter means more lensing. So if omega k is fixed to 0 because we are assuming a flat universe, we have this strange evidence for a lens larger than 1, but a lens can be 1 if omega k is less than 0. And here we have to be careful because this is just a phenomenological parameter introduced by hand, a consistency check that is failing. Omega k is not a parameter beyond the standard model, but is a parameter of the standard model because it comes just from general relativity. So now, okay, the universe is closed, not really because Planck has been reanalyzed several times and there are now new likelihoods. One of these is comes back, where the parameters is much more in agreement with Lambda Cold Dark Matter. But unfortunately, the temperature problems are still there. As you can see, even in the new release, PR4, A lens is larger than 1 and more than 2 sigma, omega k is still less than 0. And as you can see here, okay, they are ruling out omega k equals 0 with the same probability, okay, the different release, the dashed line and the solid line. What has changed is the polarization, the blue line, and now the average value is more in agreement with a Lambda Cold Dark Matter model. But what is the price? First of all, we are introducing an internal tension of the value of sound horizon of the angular size of the sound horizon at recombination. That is a quantity that is very well measured by LCMB. So from the polarization, this is shifting away from the temperature value at the level of 2.8 sigma, assuming Lambda Cold Dark Matter, but becomes 3.2 to 3.3 sigma for if we introduce a lens fit to vary or a curvature. And also, if we now look at the reduced chi-square, we see that the Lambda Cold Dark Matter model best fit is in disagreement with the data at the level of 4.5 sigma. So it's true that this new likelihood can solve the aliens problem, but this is just because of an average effect, and we are doing that at the price of introducing an internal tension and a worse fit of the data. Now there is also a new likelihood that is Hilly-Pop that seems to solve again the lens problem. Unfortunately, none of these can solve the Hubble constant and the AC tension at all. So another problem another curiosity is the value of the optical depth, because what we try to test if this can be related to the tension and anomalies we see on the data. Okay, the optical depth is a sort of a second scattering surface, and this value of the optical depth can be measured through the bump in the polarization at a low multiple in the low multiple region, or through the combination with the amplitude of scalar primordial perturbation in the damping tail of the temperature power spectrum. What we see is that this value changed a lot from WMAP to the new Planck release. And this is because of a better understanding of the foregrounds, a better measurement, but the error bars went down, and in this way also the error bars on the other parameters, the Hubble constant, went down. Now, this value is very, very small. So if there are undetected systematics or foregrounds, it's very difficult. Okay, this can have critical effects on the other parameters. And also we discarded completely the cross correlation between temperature and polarization on low multiples because they were having an excess of variance compared to simulations. So what we try to do is to test if we are going to fit, okay, this is the low E multiple data that we use to derive the value of tau that we use as a baseline every time we do an analysis of the CMB data. What we try to do instead of fitting, okay, the functional form that we expect if we have this optical depth, so the reionization bump, to use a flat line, that is the green region here, and you can see that this is compatible with the data with a p-value 0.063. And if we focus just on the region up to multiples 15, where there is the polarization bump, and we try to fit this with no signal at all, this is still in agreement with the data at the level of 1 sigma. So we have to be very careful in just having one measurement of the optical depth. We should understand if this has an effect on our cosmological parameters. And actually it has, because if we remove this low E region completely, we see that we have no more problem with the lens, no more problem with omega k, and no more problem with the phantom dark energy that we usually have in the Planck data. So it's possible to have a different estimate of the optical depth. Yes, we can do that if we consider a combination of CMB data with CMB lensing data and BAO and supernovae data at the same time. So from Planck, we have this new estimate considering, okay, just the damping tail with low redshift data. And from ACT, this other estimate. They are in agreement with each other, very compatible. And they are in agreement also with the value from Planck using the low E data, the level of 1.8 sigma. And if we now use the new estimate of the optical depth, we see that there are no more anomalies and new physics coming from the Planck results. So now we can say, okay, let's discard Planck. Let's see what happens with the other alternative CMB experiments, because we don't trust Planck anymore. But unfortunately, also ACT has a problem. Okay, I don't know if we want to call this problem, but actually it's measuring the scalar spectral index exactly 1, so Harrison Zendovich power spectrum. This is favored by an Occam's razor point of view, because as one less parameter is in tension with the value measured by Planck. And okay, that something that has been proposed is okay, but we are not measuring the first 2 peaks of ACT, so this is why we can't really measure well the spectral index. So we try to remove the first 2 peaks from Planck, and we see that we can measure the scalar spectral index accurately well, and this is still in disagreement with an Harrison-Zendovich spectrum at the level of 4.3 sigma. If we have an Harrison-Zendovich spectrum, since there is a positive correlation between the scalar spectral index and the number of E-folds, with ACT, we are ruling out all the benchmark inflationary scenario like Starobisky and Alpha Tractor. And this is happening because, okay, there is this strong tension between Planck and ACT that is above 3 sigma if we add the large structure information like BAO and weak lensing data. And in the plane scalar spectral index baryon density. And this is above 3 sigma if we look at the whole volume of the parameter space using the suspiciousness statistics. This is the level of 2.6 sigma. So these are 2 experiments that are looking at the same observable, assuming the same model, and they disagree. And if 2.6 sigma seem not that much, assuming a Lambda Cold Dark Matter model, this is creating a lot of problem for the extensions, because, for example, something that wasn't working for Planck, like early dark energy, now is more than 3 sigma evidence from ACT and can solve completely the Ableton and constant tension. The inflationary sector is completely different. From ACT, we have 2.9 and 2.7 sigma for a rounding, and a rounding of the scalar spectral index that for Planck are exactly equal 0. And we have also an indication for a total neutrino mass different from 0 at the level of 2 sigma, that is completely in disagreement with the strong upper limit that we have from Planck. Is more in agreement with the value that we have from Planck, assuming that the lens is a systematic and marginalizing over this parameter. So now if we want to try to solve the SMB tension with like simple extensions, what we see is that we need an effective, the only possible extension that can solve the tension between ACT and Planck below 2 sigma is assuming that we have an effective below 3. That means ruling out that our neutrino have a strange neutrino sector with low temperature heating. So this is my conclusion. From my point of view, okay, data sets now are very mature, and the teams are working hard on the data sets. So probably the tensions and anomalies we see is that because we are assuming a Lambda Cold Dark Matter model, and the point is not solving H naught is very easy. The problem is solving H naught at the same time. Be careful with the sound horizon, so be in agreement with the low redshift data. The S8 tension, be in agreement with the weak lensing data. The correlation between the parameters and possible fake detection, so we should always check with forecasts, mock data sets if what we see is real. The hidden model dependence some of the data sets, so we should be careful when we use the data sets as they are. We should always question if they can be used. The possibility that the problem is on the CMB side, so the Planck A-lens problem, the role of the optical depth, the fact the CMB experiments now disagree on the different on the value of the parameters. And now there are the new DESI-BAO data, okay, that are adding an intriguing twist to the situation. So something that when I started my PhD, we were saying to do that we were going to do precision cosmology. So we were testing fundamental physics with cosmology. Now I think that this is very is unlikely to be the case because there are all these discrepancies. So we probably need new observation and new investigation of alternative theoretical models and solutions. So I will leave you with this advertisement. We have this cost action called Cosmoverse. We are working, trying to solve the tension, and everybody welcome to join. Thank you so much.
Let's take questions from the audience on Zoom as well. Folks on Zoom, you feel free to raise your hand and I'll call on you to ask a question. Next, please.
Thank you. That was a comprehensive review, and a lot of it went very fast. I want to ask you one bit that I just didn't catch. This thing called IDE, interacting dark energy.
Yes.
What exactly is the idea? What is the interaction? What is it interacting with?
Exactly. So, okay. So, first of all, this is just phenomenological. Okay. So, there is unfortunately no theoretical model that can explain this. So, it's the dark matter interacting with the dark energy. So, we can have a flux of energy between dark matter and dark energy. Now, we just modify the conservation equations, okay, assuming that there is this flux of energy between these two components. And the rate can have whatever different functional form you like, but the only one that works to solve the Hubble constant tension is this one, and unfortunately there is absolutely no theoretical explanation for that. So yeah, I like to this example not because it works, okay, but because it like okay, it make us ask more questions about the reliability of the data, the fact that we need to cross-check with simulation. So this is just a working example, has no theoretical foundations at all, but it works very well. And so at this point, maybe we should change our way of doing the data analysis and extract the data. So yeah.
Yeah. So it has one fitting parameter psi.
Yes.
And I think you found that minus 0.4 works.
Yes, exactly. Okay. Yes, this is the case.
Okay.
Okay.
Thank you.
So, yes, the growth structure here is completely different, and we are trying to do n-body simulations for this model to be able to analyze from the beginning and extract from the beginning weak lensing data and BAO data and see if using everything in a consistent way, we find different results. And we will use this as a working example, okay, like for possible modified gravity scenario or whatever will be suggested in the future for solving the Hubble tension.
Priya, I see your hands up. Do you want to go ahead?
Thank you. Hi, Eleonora. Thanks for a really nice talk. So I had a very similar question. So this IDE model, if you are able to calculate for this best fit parameter, there should be many other observational predictions that you could test. For example, even the abundance of halos is likely quite different, right? So I was just curious about whether there are some other simple kind of analytic before you can do a simulation estimates that you can do that could maybe rule out the model. And this is in the context, it looks to me, Eleonora, like from all the models and things you've tried out, is that basically we need one more parameter, right? So if lambda CDM, we can add one, if we have the freedom to add one more parameter, it looks like we don't have to change anything fundamental, right? About the theory itself.
Yeah, okay. So first of all, from my point of view, okay, we have 95% of the universe that we don't know because we have dark matter and dark energy. So I find very easy to think that something like an interaction between these two quantities can happen. So, but every time you change this functional form here, if you put here dark matter, or this is I don't know, dynamical, or you have combination of them, this is not solving the Hubble constant anymore, okay? So the Hubble constant tension. So you need exactly this combination here, and it is very difficult to obtain from a theoretical point of view. Now, the key here is that you are lowering the value of the matter density today. So in this way, you have a higher value of the Hubble constant. So with your one additional parameter, you can obtain this. This can work very well in solving the Hubble tension. Now, this model, okay, has been only analyzed until now, CMB data, BAO data, supernovae, redshift space distortions. The problem is that some of these observables actually are assuming Lambda Cold Dark Matter. So since here in this model we expect a growth structure that is completely different, we should understand if we can use these data sets as they are. And this is the work we are doing. Now we possibly will be able to rule out this model completely. The prediction for other observables, there are not predictions in the literature, and I don't think that there is enough interest in the model to do this kind of predictions. So let's see.
Yeah. No, thank you. So it looks like, if there is some way to just dilute omega matter at late times, right? Say at redshift 1 point below 2, basically, it looks like that could bring things into alignment, right?
Exactly, but if you here put omega matter, okay, and you try to do the same thing, so if you have less matter today, it doesn't work. Okay, it has to go as quick as this is predicted from this formula here. And you can have also the, I don't know, like the Cold Dark Matter. There are models like that. They work, but they don't work enough.
I see. Okay.
Okay, thank you.
Thank you so much. Yeah.
Okay.
I have a naive question. What is the claim about all the current model fitting the two data, one from S8, the other one from the...
What is the claim about the model fitting the two data?
Yeah.
Which data?
So you mentioned there's an S8.
Yes.
There's another one, which is the H0. And you made a claim, I believe early, that there is no current model that fits both data well.
This one, you mean?
Oh yeah, this page, sorry.
Yes. Yeah, okay, so this is because, okay, when you solve the Hubble tension, you usually have two possibilities. You modify the expansion history before recombination or after recombination. If you modify it before recombination, you are also modifying the sound horizon. And if you modify the sound horizon, and it is this plot here, you modify the sound horizon, you are moving along this line of correlation for the CMB. So this is true, okay, the different slope is because actually, okay, when you compute the angular size of the sound horizon, the angular diameter distance, they're computed at different redshift. For the CMB, you have redshift 1100, for BAO, you have redshift about 1. So the slope is different. So now you are, when you measure the omega m h square from the CMB, you are moving along this line of correlation in this way. So solving the Hubble tension, at the same time reducing the sound horizon for early solution, you are preferring naturally from CMB an higher value of omega m h square. So this means that you are in this plot here, in this plane here. So you are exacerbating the S8 tension. And this is a problem for the early solution. For the late time solution, you have this other kind of problem, okay? You just can increase H0 whenever you want, but you can't move the sound horizon because the sound horizon has been formed at recombination and doesn't change anymore. So yeah, so that's the conclusion, okay? So if you find a model, if you try a model, if you propose a model, you should be able at the same time to fit these three quantities in a perfect way. So lower S8, lower the sound horizon, and increase H0. And none of the model works well in doing that. So the models can do two things at the same time, but not the third one. So it depends then where there is your threshold. Okay, there are many models that can do this well around 2.5 sigma, but for sure none of them can do this at like 1.5 sigma or below 2 sigma.
Thank you for this wonderful and synoptic tour of the difficulties. It looks, I mean, from outside, it looks like we're both stymied at the observational level and on the theoretical level. So if if we don't have a cosmological, even parametrizable alternative, and the observational data is in conflict, do you have a sense, having thought about this range of difficulties, where the weak point is? Something's got to give, right? I mean, it's either got to be observation or theory. Yeah, I mean, where do you end up?
Yeah, that's a very good question. Unfortunately, I'm very negative and pessimistic by by nature. So, okay, what I see is that from astrophysical point of view, they're doing their best. Okay, they are analyzing the data and they are cross-checking, and there are different teams working on that. So, it's true that okay, historically, astrophysical measurements are more prone to systematics, but they are really working hard. On the CMB side, I don't think that there are people working that hard as well, okay? We just assume that the CMB is linear, everything is perfect, so we believe to the CMB more. But the CMB is Lambda Cold Dark Matter dependent, in general, cosmological model dependent. So we will always have the problem that we can only compare models from a Bayesian point of view. We just do model comparison, so we can't really say this is the exact solution. We can say this is more likely solution. So what we really need is alternative ways of measuring these parameters. So we hope in the gravitational wave standard science that can have an independent measurement of the Hubble constant that has nothing to do with all of this. So at that point we can say, okay, this is the true value. And also, okay, from my point of view, what we need is another satellite experiment like Planck, because it's true that there will be light, but that this will be doing just the very large scales, and then to combine with the small scales, we need something on the ground, and then you have problem of cross calibrations, and we already see that from the ground, okay, we have this scalar spectral index equal 1. So the best would be if I had a lot of money that I could do stuff, do a new satellite CMB experiments to understand if what we see was a statistical fluctuation or is actually indication for new physics, and new experiment that can measure things independently, so gravitational wave standard science, for example. But more than that, I don't think we can do.
Thank you.
Thank you so much.
Let's just take a couple more. Fabio, did you have a question? I saw that you turned your video on. I didn't know if that indicated. No, okay.
No, I was just participating.
Okay, wonderful. Yes.
Yeah. I wanted to mention that in principle, it's true that cosmology, that BO analysis depends on the assumed cosmology. But yeah, I wanted to add that it's actually twofold. So one is the cosmology used for, which we kind of in DESI termed internally grid cosmology, used for coordinate conversion from sky and redshift to 3D Cartesian. And the other one was template cosmology, used to generate the shape of the BO signal. Yeah, and it sounded like you were more concerned about the grid cosmology part, which I suppose is because you were talking more about late time solutions at the time, and so it makes sense that the shape of the BO formed in the early universe doesn't change, but it could be relevant for the early time solutions as well. And when we did an analysis on one of technically such models with different pace of recombination due to baryon clumping, possibly due to primordial magnetic fields or something else, we did check if the BO template changed significantly, and it didn't. Although it is not obvious how it happens for other models.
Sure. Okay. The point is not that, of course, okay, there are the BO has been checked extensively, changing the model and see if the results are still reliable and the data can be used as they are. My problem is that the reliability is always done around Lambda Cold Dark Matter, and we go far away as much as 5 sigma. That is nothing for models that can solve the Hubble tension, because here I have a model like the interacting dark energy, that is giving this kind of interaction, minus 0.4, okay? Oh, this is the wrong button. So for this kind of model, the growth structure will be completely different because there will be a friction term, then it will be accelerating, okay? So are we sure that the BAO data, as we know them, around Lambda Cold Dark Matter 5 sigma can cover this kind of models? And I'm not sure about that. And of course, there is not enough, as I said, interest in this kind of models to convince the BAO community to test points that are very far away from Lambda Cold Dark Matter. If we can do that, of course, this is increasing the reliability in the data, and we can safely say, okay, we are ruling out all of the late time solution. Well, that's not true because, as I said before, okay, if you have strange dark energy, negative dark energy density, that's not completely true, but at least a good class of models. As far as I know, okay, talking with people, this kind of tests for very strange models has not been done. And yeah, I think, okay, now I'm trying to do that with my PhD student. I don't have the skills, so we are working with VO people, people working in the biodata analysis to understand if it makes sense and it can make a difference. But yeah, so that's my point. Okay, let's see what is going on.
Yeah, totally agree. Also, yeah, I guess from the point of view of BO community, yeah, there is what the BO data is telling us, and it's not super plausible, I suppose, to think that there is some huge deviation. So, like in the C, we only tested not very far deviations based on the expected error bar, more or less. Although, yeah, it might in principle be possible that there is some wild variation which somehow still brings BO analysis in close agreement, but hasn't been considered because the model is just too exotic.
Exactly, that's the point, okay? So since here we are looking for solution of the Hubble tension and nothing of the simplest possibility is working, so you have to think exotic. And at that moment, if we think a very exotic model, are the BAO still can still the BAO use as they are? I don't know anymore, okay? From my point of view, from a model point of view, I don't know anymore what to do because standard things don't work. So let's think exotic. And at this point, I have to start to question the reliability of the data. And this is why, okay, we start to use the 2D BAO because we said, okay, the error bars is much larger, so we will be more conservative. And we see a shift in the parameters, okay? This is what I was showing before. When we assume Lambda Cold Dark Matter, there is no shift. But if we assume interacting dark energy, there is a shift. So it seems like there is something. Maybe it's not significant, but okay, I think that should be tested, at least.
Okay, I think we'd better wrap up. Thank you so much, Eleonora.